So we're going to now look at an alternate version for the equation of a plane in 3 space. And this one's called the Cartesian or scalar equation of a plane. So take a look at the following diagram. If you let P0 represent a known point, and P represent a general point on the plane, and N represent a normal to the plane. And all a normal is a vector that's perpendicular to all vectors in this plane. So this normal vector is perpendicular to the plane. Well, let's take a look at what happens if I dot this normal vector with P0P, or vector P0P. That's this one right here. So I'm going to take the normal N, and I'm going to dot it with vector P0P. And if I do that, I should end up with 0, because the vector N, or the normal, is perpendicular to all vectors in the plane, and P0 and P are 2 points in this plane. So from our note there, we see that the normal has components A, B, and C, and I'm going to dot it with P0P. Remember, P is a general point x, y, z, and P0 is a known point x0, y0, z0. So if I do OP minus OP0, I get x minus x0, y minus y0, and z minus z0. And that all equals 0. If I dot these two vectors, I end up with A, x minus x0, plus B, y minus y0, plus C, z minus z0 equals 0. If I expand this expression, I get ax minus ax0, plus by minus by0, plus cz minus cz0 equals 0. So now I'm going to split this into 2 parts. I'm going to take the terms with x, y, and z and put them together. So I have ax plus by plus cz plus the remaining terms, negative ax0 minus by0 minus cz0, and that all equals 0. Remember that x0, y0, and z0 are a known point, and A, B, and C is the normal to the plane, so that is also a known value. So all this is known. It's a known point with a known normal to the plane. And if that's all known, that is going to be a constant. And what I'm left with is the following equation. AX plus BY plus CZ plus some constant, we'll call it D, equals 0. And this is what we call the Cartesian equation of a plane in 3 space, where A, B, and C are the values or the components of the normal to this plane. Let's take a look at how to use the Cartesian or scalar equation of a plane to solve various problems. So example 1. The point A, negative 1, 2, 0 is a point on the plane, and the plane has normal 3, negative 2, negative 2. So we have a plane. We have the point A on the plane, and we have the normal to the plane, so a vector that points perpendicular to all vectors in this plane. So if I want to determine the scalar equation of the plane, I start with ax plus by plus cz plus d equals 0. I already know that the normal, n, is equal to a, b, c, which in our example is 3, negative 2, and negative 2. So I have 3x minus 2y minus 2z plus d equals 0. Well, all I need to do now is find my constant d. And to find my constant d, I need to replace the x, y, and z. And since we're talking about an equation of a plane, the x, y, and z represents any point on the plane. So now I can use point A. So point A is going to give us our x, our y, and our z. And for this example, point A is equal to negative 1, 2, and 0. If we sub that into our equation, we get 3 times negative 1 minus 2 times 2 minus 2 times 0 plus d is equal to 0. And then all we need to do is solve for d. And for this example, we get that d is equal to 7. So therefore, our Cartesian or scalar equation of this plane is going to be 3x minus 2y minus 2z plus 7 equals 0. So this equation represents all the points on the plane with the given normal and the given point. So part B, determine where the plane crosses the x-axis. At the x-axis or on the x-axis, we know that y and z are 0. Using this information, we see that we get 3x minus 2 times 0 minus 2 times 0 plus 7 equals 0. So right away, I can see that x is equal to negative 7 over 3. And recall, if we were using the vector equation or the parametric equations, there would be a lot more work to find this x value. So therefore, the plane crosses the x-axis at 7/3, 0, 0. So that's the point where it crosses the x-axis. So if you think of a plane in 3 space, so I'm just going to draw part of the plane. If it's angled in such a way, it could hit the x, y, and z axis. So we found this point here, 7/3, 0, 0. And C, determine any other point on the plane. Well, it's the same idea. I have 3x minus 2y minus 2z plus 7 equals 0. All I need to do is pick x and y values and then solve for the remaining variable. So for example, I could let x equal -1 and y equal 2. So therefore, I have 3 times -1 minus 2 times positive 2 minus 2z plus 7 equals 0. This gives me negative 2z, and then adding those up, that gives me negative 7, so that's going to give me negative 2z equals 0, and therefore z equals 0. So now I've found a point on the xy plane, so let's call it point B, and that has components -1, 2, and 0. So this is a point on this plane. And you can pick any x and y value and solve for z, or you can pick any y and z value. The easiest, of course, are the intercepts, so let x equals 0, y equals 0, get the z-intercept. Let y equals 0, z equals 0, get the x-intercept, and so on. Example 2. Determine the Cartesian equation of a plane containing the following 3 points. So notice in this one, I don't have the normal to the plane, but I do have point A, point B, and point C. And if I want a vector that's perpendicular to this plane, if I take 2 vectors on my plane, let's say AB and AC drawn here, if I want the normal to this plane, the normal would just be the cross product of vector AB crossed with vector AC. Remember, the cross product gives me a vector that's perpendicular to a plane, and its direction is based upon the right-hand rule. So therefore, n is equal to AB cross AC. Our components for AB, so it's going to be OB minus OA, is going to be 4, 0, and -1. And I'm going to cross that with the components of AC, so that's OC minus OA. So that's going to be -1, -5, and 1. Next up is determine our cross product. And from our cross product, I get 0, so I get -5. And then I get 1 minus 4, so that's -3. And then I get -20 minus 0. So far we have that our plane is -5x minus 3y minus 20z plus d is equal to 0. And now I should be able to take any of these 3 points and determine the d value. And they should all give me the same d value. So let's take the first point. Let's sub in point A. So for point A, I get negative 5 times negative 1 minus 3 times 2 minus 20 times 5 plus D equals 0. And if I solve for D, I end up with 101. So you end up with the equation of a plane that looks like negative 5x minus 3y minus 20z plus 101 equals 0. Here are two key points when considering equations in Cartesian form. So first thing, the leading coefficient should be positive, and the second thing is that you should reduce or simplify if possible. So imagine this was 10x, 6y, 40z, and 202. You should be able to divide everything by 2 and simplify the expression. So for these examples, we should all have the same equation for our plane. So for this one, all we need to do is multiply everything by negative 1, and we get our plane is 5x plus 3y plus 20z minus 101 equals 0. So please remember those 2 points. Leading coefficient is positive, reduce or simplify if possible. And our final example. Determine the angle between the two planes shown here. So here's plane 1 and here is plane 2. So I'm going to try to explain how we can find the angle in a few simple steps. So I'm going to draw a side view of the two planes intersecting. So let's say this is plane 1 and this is plane 2. Remember that these planes have normals. So let's say this is the normal to plane 1. So we'll call it N1. And here is the normal to plane 2. We'll call that N2. Here is the angle we're looking for. We're looking for this angle here, the angle between the two planes. Remember the normals are perpendicular. And notice we have a quadrilateral here. This angle here, we'll call it alpha, has a relationship with theta. You should note that alpha plus theta has to equal 180 degrees. Well, if that is the case, this angle here is also alpha. Notice that if I take alpha plus theta, that is also 180 degrees. So if I can find alpha, this angle here, I already know the angle between the two planes. Why am I using this one? It's because I know the normals. Using the normals, I can find the angle between two vectors using the dot product. So if I want the angle between two planes, I can use the angle between the two normals to find the angle between the two planes. So remember the dot product states that if I take N1 and I dot it with N2, that's equal to the magnitude of N1 times the magnitude of N2 cosine theta. So we note that the normal for our first plane is 2, negative 1, and 1. The normal for our second plane is 1, negative 3, and it's missing the z, so that's going to be a 0. Since we know the normals, we now know their magnitudes. So the magnitude of vector n1, remember that is the square of 2 plus the square of negative 1 plus the square of 1, which is equal to the square root of 6, and the magnitude of n2 is equal to the square root of 10. All I need to do now is dot these two vectors and solve for the angle. So n1 dot n2, so that's the left side of the equation. That's going to be 2 plus 3 plus 0. So remember that is this times this, plus this times this, plus this times this. That's our dot product. That's equal to the magnitude of 6 times the magnitude of 10 cosine of theta. So if I want to solve for theta, that's going to be the cos inverse of 5 divided by root 6 root 10. And therefore the angle between the two planes, or the angle between the two normals, is equal to approximately 50 degrees. So again, based upon this diagram, if you have any questions about this diagram, please let me know. But again, we have a quadrilateral formed by the two planes shown on their side and the two normals. And we see that alpha, the angle between the two normals is equivalent to the angle between the two planes. And then using the dot product, we can determine the angle between the two normals, which equals the angle between the two planes. So here are some questions that you should try, and good luck.